Hey, what's up everyone? Jason Turley here, back again with more ROP Emporium. We're cruising along and we're going to knock out challenge 5 today. It's titled Bad Chars or Bad Characters. So learn how to deal with bad characters or characters that will not make it into the process memory intact or cause other issues such as premature chain termination. So typical bad characters, off the top of your head, you probably can already think of a few. Things like the null bytes, things like the new line character or character return values, any type of white space basically, or anytime you hit enter, especially that null terminator, because a lot of the times the functions that we're exploiting are things like stir copy or stir cat, any of these C library functions that work with C strings will stop reading after the null terminator is there. So I'm curious how they're going to implement bad characters and what type of mitigations and workarounds we'll need to do. This typically comes into play when you're generating like your own shellcode. So let's say you exploit a binary and you use something like MSF Venom to craft your shellcode for you, whatever that may be. It might have some bad characters in there that you need to explicitly filter out. So let's see what we're working with. So the good and the bad. Dealing with bad characters is frequently necessary in exploit development. You've probably had to deal with them before while encoding shellcode. Bad characters are the reason that encoders such as Shikata Ganai exist. When constructing your ROP chain, remember that the bad characters apply to every character you use, not just parameters, but the addresses too. To mitigate the need for too much reverse engineering the binary, we'll list its bad characters when you run it. So that's nice. So it gives us some options. So ROPper, and we saw that in our last video, we used ROPper. It's just a tool to find ROP gadgets for you. They have a bad character option to help you avoid using gadgets whose addresses will terminate your chain prematurely. It will certainly come in handy. Note that the amount of garbage data you'll need to send to the ARM challenge is slightly different. Well, we're not working with ARM. So more XOR. Still need to deal with writing a string into memory, similar to the previous challenge, that may have bad characters in it. Once your string is in memory and intact, just use the print file method to print the contents of the flag file. Just like in the last challenge, think about how we're going to overcome the bad characters issue. Should we try to avoid them entirely, or could we use gadgets to change our string once it's in memory? Helper functions. It's almost certainly worth your time writing a helper function for this challenge. Perhaps one that takes as parameter a string, a desired location in memory, and array of bytes. Or array of bad chars. It could then write the string into memory and deal with those bad characters afterwards. So yeah, that's true. Whenever you do any type of like real programming or software engineering, it's good to have helper functions, just things to take care of like certain issues or tedious, repetitive tasks that come up. We're just writing a simple script. I don't know if we'll need the helper function. So I'm coming to my terminal and you see that it already has some code in here. This is from the last video. So I'm using tmux so I can open up multiple panes. And right now you just saw that I opened up like my second pane. And I can also like rename some of these. So instead of calling this bash, I'll call that write4 because that's from the previous episode. And maybe I'll call this one like bad chars. So let's actually start downloading this. So wget this file, unzip it, specify the output directory is bad chars, ls, remove that zip file because we no longer need it. And now we can cd into this directory. So just like last time, we have the flag file, we have something called bad chars, and I guess this is the shared library. I'm not going to analyze it a ton because it does get a little bit repetitive and it does make the video a bit longer. So here are the bad characters: X, G, A, and period. Interesting. So please sub. And it says thank you. So let's open this up in GDB. And let's disassemble the main function. Okay, it calls pwnme. Let's disassemble pwnme. And I guess the address isn't resolved yet. So let me just set a breakpoint there and run it. Now let me disassemble pwn.me. There we go. So I'm not going to take a ton of time on this, talking about things that I talked about in previous episodes, or previous videos, I guess. So we see 40 bytes are being subtracted from the stack. What is OX40? Print decimal OX40, so 64. So I believe our buffer is 64 bytes long. Let's kind of just skim down and go right to the read function. So this is our buffer. It's using the base pointer, I guess, to allocate OX40 or 64 bytes. It's adding 32 to it. OX20 is 32, right? Why is it doing that? Why is it at 20? Is that moving our pointer forward? So I'm gonna clear this out. That's from the last video. It looks like it's calling read on 0, so standard input, so like standard in. And then it's doing like our buffer plus 32, and it's reading OX 200 bytes. So it's probably something like character buffer 64, like a 64 byte buffer, and it's setting that equal to like 0. But then we're moving 32 bytes in, like we're moving halfway in, if I'm understanding this correctly. So it calls read, and now I think it's actually looking, at some point it has to look for the bad bytes. Is that a helper function? I see OXEB here. What is that? I'm sure I can do this with RAX. Maybe. I always forget the flag. Is it I? Oh my goodness. I'll just do it in Python. E. When is it actually checking for those bad bytes? Let's see, does some comparisons. Let me analyze this function a little bit. Let's do robin to tac capital I on bad chars. Okay, let's do lowercase I. pwn.me and print file. Those are the only functions it's calling. What about that shared library? I'm looking to see if there's like a bad chars function. It looks like it's doing everything inside of pwn.me itself. If we scroll up to the top, it told us what the bad characters were. X, G, A, and then like period. X, G, A, period. RAX2. So we should see bytes 78, 67, 61, and 2E. Do we see those at all? Do we see OX78? I'm just curious, where and when is it checking for these bad characters? Could be right in front of me and I'm just like missing it. This is not the correct solution, but I'm curious. If I copy over my exploit from write 4, well, it won't have the same ROP gadgets, but it'll be a nice template. So let's continue. All right, those are the bad characters. Let's actually quit out of this. Pattern, create 100. Grab the string, run it, hit C to continue. Those are my bad characters. Oh, it doesn't like A, but let's just hit it. Let's just see what goes on. It's seg faults. It looks like it took out my A's. These are all EB and everything. Where is it doing that logic? Where is it doing the comparison to see what I enter? Here we can kind of see that there's like some type of loop going on. We see add RAX1, and then it compares. And if it's lower, it jumps back up to 160. So I think this right here is some type of like for loop, where it's like iterating across each of my user input, everything I put in the buffer, and it's doing the comparison. I could open this up in Ghidra to like decompile it, but I don't know. I don't feel like opening up a whole Ghidra project for this. But so we know these are the bad characters. Is there like a useful function or like a useful gadget? Useful function, okay. Useful gadget. Why are we doing XORs? I'm not sure how useful this will be. We have this one. This is very similar to the one from last video. Whatever is inside R12, store that in register R13. Let's, can we just grab this? Let's open up this exploit from the last episode. Let's change this around a bit. %s write 4. Bad cares, change the name of it. It's still going to take 40 bytes of padding. Writable memory address, VM map. Okay, so the writable address is the same. Here. So the write what where is now this. Let's change the comment because this is no longer relevant. This will be R13 plus OX0. So it's an offset with an R14 or R13, but it's 0. So it's the beginning of R13. So now we need like pop R12 and pop R13. Let's get that address of print file. Okay, that actually didn't change, so that's good. Let's exit out of this. Let's do ROPR file bad cares. Search for pop R13. Okay, so 13, 14, 15. What about R12? Oh, okay, so that's good. I also need the bad characters. Bad cares, X, G, A, and dot. How do I specify bad characters in ROPR? ROPR, tac help. Tac B, bad bytes. Set bytes which should not contain. So tac B. What do I have? RAX2 sec S. XGA dot. I specify it like this. Okay. So let's grab this address. This is very experimental. Not really sure if this will like give us what we want. But sometimes that's just the nature of like exploit development. You got to play around with it. You're not always going to get it at the very first try. So let's change this. So pop R12, R13, R14, and R15. So the name of these variables don't really matter. It's not going to change how the program flows or executes, but it will help like me logically kind of understand and make sense of what's going on. So let's do ROPR again, specify those bad characters, and we need a pop RDI instruction. Nice, we got it. Is that the same? The address is changed. Just gonna grab this, copy it here, change it here. So I think that's majority of what we want, right? The only thing that's really changed in this is like those bad characters. It's still going to take 40 bytes to overwrite the base pointer and the stack, the base pointer, and then get to the stack pointer. We can reuse the same writable address. Now we want to pop inside R12 and R13. We have to pop some junk as well for these. Pop RDI. That's the same. So this is changed now. So R12 will contain flag.txt. R13 will contain that memory address. And now we need like junk for R14 and R15. 1, 2, 3, 4. 1, 2, 3, 4. Let's do that twice. Write what where? So take what's in R12, flag.txt, store that inside R13, pop that same address inside of RDI, and then call print file. Okay, so let's run this, save it, and let's run it. Ooh, we get an error. Can't decode byte EB. Let's take out the decode, I guess. It doesn't sound like it worked. It doesn't sound like it's going to work the way we want it to. Thank you, failed to open file. Oh, you know what? Ah, man, A is a bad character, and we have that in our string. We have A, and we have period. So maybe that's where the XORs came into play. Let's see. Let me make a dummy file. Echo, this is a test. Call it foo. Instead of flag.txt, let's just try to open up foo. It didn't fail. Bad chars stopped. Does the file need to be 8 bytes long or 8 characters? Move foo. One, two, three, 4, 5, 6, 7, 8. Python exploit. I don't know. It's not saying it failed. It's not printing anything out. Oh, I keep adding A. I keep adding these bad characters. Let's just call it 1, 2, 3, 4. 1, 2, 3, 4. I know this looks terrible. But that doesn't contain any of those bad characters. Now run it. It says thank you, but it never actually prints out our contents. Why? Why isn't it printing out what we want it to? Let's attach it to the debugger this time. Set a breakpoint on pwnme. Run it. Disassemble. Let's set a breakpoint on that read. Pwnme plus 141. Delete that first breakpoint. Continue on. So this is the contents of the stack and the registers before our user input is received. Hit NI. Ooh. We're not overriding the stack pointer. Did the offset change? Let's quit out of here. GDB bad cares. It's always 40, but did it change? Pattern create 100. Let's see. This might not work because these have A's in it. Run. Slam that in. Pattern search. $RSP. Can't be found because the pattern has changed. Let's exit out of this. Let's do Python. Let's do A times 40. And let's do like B times, I don't know, 30. Let's rerun this. Let's give it this string. So it overrode it with B's. Examine string $RSP 30 times. So it does take 40 bytes. It does take 40 A's. Because our 30 B's are written here. So when I run my exploit, set my breakpoint, continue. Why are these not overwritten? Why is it starting all the way down here? It should be executing from the top of the stack. Gigs hex from the stack pointer. Okay. We see the 40 bytes of A's. Let's move it over here. Let's look at these side by side. So we see our 40 bytes of A's being written, and then this should be the pop instruction. Yeah. Here's the name of the file, the placeholder. Here, what am I popping into this? So R12 is the name of the file. R13. So this should be the address. This shouldn't be junk. This should be data address, right? Here. Is that the issue? So R12 will contain our name of the file. This is just a placeholder. R13 will contain the data address. 14 and 15 we don't need, so we have those called junk, and then the write what where. So let's quit out of this, and I guess we'll just make a new terminal. We'll rerun it. Set our breakpoint, continue, NI. It still starts all the way down here. I don't know why. I don't know why these bytes are not being overwritten. But let's examine the stack pointer. So this looks better. It looks a lot better. Just hit C to continue. You get a seg fault. But it does print out our file. It does print out this is a test. But if I change this, if I take out this like dummy placeholder and I leave it as flag, we get failed to open file, FL, and then our A's were overwritten, our A, G, and the dot. So all of that was overwritten. I see. So those are bad characters. Do I need to XOR them? We saw an XOR, didn't we? Okay, so if we look back here, we do see that there is an XOR instruction for the registers R15 and R14. And so that's leading me to believe, hey, maybe we don't just need this write what where with the move. Maybe we also need to XOR the bytes. Because if the bad characters, and I guess we can just run it. If the bad characters are X, G, A, and period, which do exist in flag.txt, so I'm guessing we can give it like some type of jumbled up value and then XOR it. And after it's XORed, it'll be flag.txt. So we want to bypass this bad characters check, essentially. Let's just exit out of this. Exit. So I'm back inside my exploit. And let's see if I can clean this up a little bit, make it a little simpler.
2,000 years later.
Okay, so continuing to clean this up a little bit. I might need to get rid of these instructions like entirely. We'll see. But the main thing is we need to XOR that flag.txt string. So let's just make a function to do that. Call it XOR string. It'll take a string and some type of key as a parameter. And what does it need to do now? We need some type of like output. I don't know. Output list. So for every string in the string, what do we need? We have to XOR it, right? But we can't just say S XORed by the key. We need to make this the ordinal value. Wrap all that in here. That's our new character. And we can add that to the list. XOR.append char. Return XORed. Let's see if this actually works. XORed, XOR string, flag.txt. Let's just give it 2. I don't know. Let's print XORed. And let's comment out this. Does this work or am I a madman? Okay, so it printed out as a list. Control C. So it does XOR them. I don't want to return it as a list though. Let's open up our exploit in Sublime text just to get a little bit of color coding. This should be a little prettier to read. Cool. So we have our XOR function. So this will XOR flag.txt. XOR flag with any key to remove bad bytes. Bad chars. Okay. We have our ROP gadgets defined here in their own section. We do need to go back and grab that XOR gadget. So disassemble useful gadgets. We do want this. We know we're going to need to XOR. Let's add it here. XOR R15 with R14. So the first stage, write the XOR data to the address. It might not like this if this is a string. Is it just encode? So now it's a byte, junk into R14, and we know we need junk into R15. R12 has the XORed string of flag.txt, and then R13 has the address, has the memory address. Cool. So now we have to inverse this XOR. So I'm curious, this XOR, it might only do 1 byte at a time, right? I don't know if it'll do all 8 bytes. But let's, I guess let's test it out. If we have to, we can do a for loop. But let's see. I don't know how many bytes it'll do. I don't think it'll do all 8 bytes. It might only do 1 byte. We still need to use this pop instruction. So the XOR needs register R13 and 12. No, it needs R15 and R14. So these two can be junk. Junk for R12, junk for R13, and then R14 will be our key. P64 key. Do I have key defined? I hard coded as 2. Key equals 2. That way we're not just hard coding things. R14, what the heck? Stores the key. And now R15 will have that data from earlier. I think it'll just be this, right? That same XOR data. It would be the actual data address. So go to the address that is in R15 and XOR it. So when we dereference R15, the first byte will be the XORed F. So R15 stores the XOR data. So now that everything's in place, we need to do the actual XOR effect, the XOR operation. And this will need to be wrapped in a loop because it is a pointer. Let's see. Do I have this written anywhere? I thought I had the output somewhere. I guess not. But essentially, we're going to have a character pointer. It's going to be flag.txt. We're going to XOR it with a value of 2. I don't remember exactly what it was, but let's just say it was like something like this. Let's just say it was something like that. So in the first run, since it's a pointer, it'll be index 0, which would be n, and it will convert that back to an f. On the second run, or we're only doing one run, so we need to do a for loop with an offset. Tab, so let's make this a for loop. For I in range 8. Was this run number of times? It has to be data address plus I. Not sure if that will fail. Let's take this outside the P64. And let's wrap it here. I feel like this code is just getting uglier and uglier by the second. So I apologize, guys. That's what I get for trying to do this live. Okay. And then this just calls print file. So this looks a little bit gross. Let's set this for the debugger. So I want to actually see what's going on. So let's quit out of this. Let's run our exploit. And it should open us up in a debugger. XOR R15, R14 is not defined. Here we go. So it prints out this. That's what I was trying to get at earlier. So it should loop through and re-XOR these into the original values. So R15, R14 is not defined. Oh, I never actually added the I never did this. P64. There we go. No, I don't want to purchase. Come back here, exit out of this. Now let's rerun our exploit. Make sure there's no errors. There is. Can't concat integer to bytes. Line 56. So go down to line 56. Okay, I changed that up top, so I have to make this the correct format. Exit. Rerun. Come back here. No errors yet. Let's set our breakpoint and run. So I did not call read yet. We're hanging right there. So I'm going to do an I to set forward one instruction. Ooh, it's just hanging. That's not good. That's not good at all. What did we mess up? It shouldn't just hang. It could just be running this function, but it shouldn't take that long. Let's come back here. Let's kill this. Quit. Since we know when we XOR it, we get this value, we don't actually have to run this every single time. So let me comment this out. Just for performance reasons, this isn't like a big deal. But let's just try hard coding this for now. XAG dot. So none of these are bad characters. That looks fine. Run it in the debugger. We have our ROP gadgets. I don't know why it's hanging so much. Maybe it's here. Let me comment all this out. Let's just see if this first stage works. Let's see if we can actually write the XOR data to the address. Let's do it one chunk at a time. Set our breakpoint. Continue. We hit the breakpoint. We step forward one instruction, and it still hangs. Why? Why is it hanging? It shouldn't. What did I change? What did I mess up this bad? Oh, I commented out this. I never actually sent anything. That'll do it. I never actually sent any data. I forgot I commented that out. Okay. Let's do it like this. So it was hanging because we never actually sent anything to standard input. Let's quit out of here. Do this again. That makes a lot more sense. I want to set a breakpoint, so I will. And there we go. So we see our data is being written down here. Again, I'm not sure why it's not written to the top of the stack. Let's do examine 32 gigs is hex from the stack pointer. And we can line this up. So this looks familiar. We know these are the addresses of like some of our ROP gadgets, and we can print that out. Yeah, so these are the pops. So this should be that encoded address, right? Awesome. Encoded address. This is our writable memory address. This is junk twice. And these are the rest of our, I guess, ROP gadgets. The move and the return. So far, this looks pretty good. Let's just hit an I to set forward a few instructions. I'm going to just keep hitting enter until we get into our payload. Okay, it's taking a bit. That's fine. My goodness. Okay, so that was taking a while. So I'm actually going to set another breakpoint. So here, and I'm going to set it outside of this like for loop. We know there's a for loop because we see here EDI is set to 0, and then we're adding 1, we're adding 1. I'm assuming it's a for loop because right here it says jump below if RDI is less than some value and go to 160. So we're just looping through all of this right now. So I'm gonna set my breakpoint here, 254. Hit C to continue. We hit our breakpoint. We can see what's going on the stack. It prints thank you, calls leave, and it's about to return. It's about to return execution to our ROP gadgets, which is great. That's what we want. Hit NI. It's going to pop, it's going to call pop R12. So it's going to put this value inside of R12. And then it's going to put that address inside R13. I'm kind of losing track of what goes where. Hopefully these are the correct values. So this is the XORed flag.txt. And then this is where we want to write it. So later on, is that correct? Yeah. I think this is exactly what we want. I might be missing a ROP gadget somewhere. Junk and junk. Okay, we're performing the write. So the value of R12 is being written to R13. That's perfect. Hit NI. Continue stepping through. Now we're performing the XOR. So R15 contains that memory address, and when we dereference it, that's when we get this XORed value. R14 has a value 2. So this should XOR it to the value of like flag. There we go. We see how this changed to an F? Awesome. That's why we need this to be in a for loop, because on the first iteration, it's just going to keep changing this F. So we have to do this address, OX601300 plus I. And I will start at 0, then plus 1, and plus 2, and so on and so forth. So it should loop through and XOR all of these. I might have it off by 1 error. I'm not sure. I think this will go 0 to 7. So now we can kind of just step through a few more times, see if I messed anything up. We're gonna do that XOR again. Oh, okay. I think I overwrote what I did. Yeah, so you see how this is an L now? That's not what we want. We want this to say an F and for this to be an L. So I'm doing something wrong inside my for loop. The for loop should only contain this. This should be outside of the for loop. Does that? I don't think that works the way I want it to. Let's see. Let me examine string, not there, from this address, OX601300. Okay, cool. So I was, I don't know, confusing myself. So we see here that this actually incremented by 1. That's why it starts with an L. We had slid over the pointer a little bit. So we do see that this is FL. Let me hit NI, and then we can continue stepping through. And we see now this is a C. If I print out from the beginning of this string, it's FLC. That's not what we want. I want this to be an A. Oh, it didn't perform the XOR yet. So now I do NI, and that's an A. Print it out, FLA. And I'm just gonna hit C to continue. It does get a seg fault, but I bet if I exit out of this, it will end up printing flag.txt. It will print the contents of that. So come over here. Where's it at? Yeah, it did print it out. ROP Emporium, a placeholder 32 byte flag. So let's come here. Let me add that decode. It makes it print prettier. Close this. Oh, actually, we need to change that. We need to change this to not run inside the debugger. And I left this hard-coded. We don't have to. I thought that was a performance issue, but it's not. So now when I rerun it, fingers crossed, it just prints out the flag. There we go. A placeholder 32 byte flag. That one was actually kind of challenging. That one was actually pretty tough. At least to me, it wasn't immediately obvious what we had to do with some of these ROP gadgets. I don't know. I don't love how the code looks. I think it does look a little bit ugly and cluttered. So let's just step through from top to bottom because it's been a long time. It's been about an hour. So here are our bad characters. It doesn't really need to be defined as an array. So the bad characters are the same on every run, X, A, G, and period. So we created a function called XOR string. It takes two parameters, whatever string you want to encrypt and some type of key. XORed is the output list. It's the where we'll store our results. So we passed in flag.txt. So for every letter, so F, L, A, G, so on and so forth, for every letter, you are going to get its integer representation. You're going to XOR that with whatever key. In this case, I picked the number 2. And then you're going to change that back to the character. So in this case, it was like D for F. And then add that to the list. And I don't want it to be output as a list. I want it to be a string because those are easy to work with. So we use a little bit of Python magic to convert our list back to a string. We set our process to bad characters. It takes 40 bytes to overwrite the buffer and base pointer. These are the different gadgets we used. Just put them all in one section so it's a little bit easier to read. And we broke this up into 3 stages logically. So we had to write our XOR data to some writable address that we have control over. You can't just leave the string like this. It has to be some type of byte. So I did .encode. Yeah, you guys watched the video. So hopefully the rest of this makes sense. And now we have to inverse that XOR string. We're really just calling XOR over and over again on every single byte that we had encrypted. So now we're just decoding it. And then we pass the address of flag.txt into RDI. And then we call print file. So not too complicated. But working from scratch, like, yeah, this was actually kind of difficult. But yeah, there you guys have it. I'm curious to see if you guys found a better or different solution in the comments down below. Hopefully this was helpful. I'm going to continue on grinding and knocking out some of these ROP Emporium challenges, and hopefully you guys find them actually helpful and insightful in any type of way. But that does it for this video, guys. As always, take it easy and see you in the next video.
Thank you.